You ever look at a really complex piece of software and just wonder, how on earth did they build that? Well, it might look like magic, but underneath it all, it's really just about relationships. Seriously. Just like in the real world, code is all about how different pieces connect and work together. And in C++, we do this with a super powerful idea called object-oriented programming. Let's dig in.
So, object-oriented programming, or OOP, it all comes down to two little phrases you already use constantly. Has-a and is-a. A car has an engine. An employee is a person. That's it. These two fundamental ideas are the building blocks we use to model pretty much the entire world inside our code. All right, so here's our game plan. We're going to start with how we model the world in code. Then, we'll dive deep into the has-a and is-a relationships. We'll even tackle a tricky little puzzle called the diamond problem. And then, we'll see how all this unlocks the true superpower of OOP, polymorphism. And of course, we'll wrap it all up with the key takeaway.
First things first, modeling the world in code. Now, before we get into any syntax, you've got to get the philosophy. See, OOP isn't just about organizing code files. It's a completely different way of thinking. It's about looking at a real-world problem and creating digital objects that act like the real things.
Okay, so let's jump into our first building block, the has-a relationship. This is all about building bigger, more complex objects from smaller, simpler ones.
The technical term for this is association. It's just when one object is a part or a component of another. The classic example, a car class that contains an engine object. The car has an engine. It's really that simple. In your code, this usually just means one class has an object of another class as a member variable.
Now this is where it gets interesting. Association actually comes in two different flavors, and it all depends on how tightly connected the objects are. On one side, you've got composition. This is a super tight bond. Think about a person and their heart. If the person's gone, the heart is too. The part can't exist without the whole. But on the other side, you've got aggregation, which is way looser. Think of a university department and its professors. If the department gets shut down, the professors don't just vanish. They can go work somewhere else. The part can exist on its own.
All right, let's move on to our second major relationship, the is-a relationship. This one is all about creating whole families of related objects.
We do this using a huge concept in programming called inheritance. It's where a child class can get all the properties and behaviors from a parent class. For example, an employee class can inherit from a person class because, well, an employee is a person. It just has some extra stuff, like a salary and an ID number.
So, what does the child class actually get from its parent? Pretty much the whole blueprint. It gets its own copy of all the parents' regular data, and it gets access to all the parents' functions and abilities. It's basically like genetic inheritance, but for your code.
And check this out. This is what it actually looks like in your computer's memory. It's not just some abstract idea. A derived object literally has a complete base object embedded inside of it. As you can see here, the child object kind of wraps around the parent's data and then adds its own new stuff. The child is truly built upon the foundation of the parent.
Okay, so this leads to a really important question. If the child gets all this stuff from the parent, are there any exceptions? Is there anything that doesn't get passed down? And yep, there are. There are 5 key exceptions here. A child class doesn't inherit its parents' special life story functions, the constructor for how it's born, the destructor for how it's destroyed, or the functions for how it gets copied or assigned. And why not? Well, think about it. These actions are unique to each type of object. A manager getting created might need to be assigned a team, but a generic employee doesn't. Each class needs to be in charge of its own life story.
Now, inheritance is incredibly powerful, but with great power comes, well, sometimes some tricky situations. Let's talk about a famous complication known as the diamond problem.
So, picture this scenario. You have a class, and it inherits from 2 different parent classes. But both of those parents inherit from the exact same grandparent class. What do you think happens then?
This setup creates what we call a diamond shape in the inheritance chain, and it causes a huge headache. The poor child class at the very bottom ends up with 2 copies of everything from the grandparent, one through its mom and one through its dad, so to speak. So when you try to use something from the grandparent, the compiler just throws its hands up. It sees 2 copies and has no idea which one you mean, so it gives you an error.
Luckily, C++ has a really elegant solution. It's a special keyword, virtual. When the parent classes inherit from the grandparent, you just tell them to do it virtually.
It's like leaving a little note for the compiler that says, hey, just a heads up, these two paths are going to merge later, so be smart about it, and only include one copy of the grandparent and the final child.
And here's the magic behind the curtain. When you use virtual inheritance, instead of cramming 2 copies of the grandparent in there, the compiler puts in just one. Then it gives each parent a special little pointer, a virtual base pointer that points to that single shared instance. Problem solved. The ambiguity is totally gone. It's a really clever fix to a tricky problem.
Okay, so we get has-a, we get is-a. We've even solved the diamond problem. Now we are ready to unlock the real superpower of object-oriented programming, polymorphism. It literally means many forms.
The magic really kicks off with a simple little trick called upcasting. So, because a rectangle is a shape, we're allowed to use a base class pointer, like a shape pointer, to hold the memory address of a derived class object, like a rectangle.
This diagram shows you exactly what's happening. We've got a base pointer, but it's actually pointing to a derived object. And this works perfectly, because remember, that derived object contains a complete base object inside of it. So the pointer is just talking to the base part of that bigger object, which it totally knows how to handle.
So why is this upcasting trick such a big deal? Because it enables the superpower, polymorphism. It means we can write one piece of generic code, like a function that draws any shape, and then we can give it a pointer to any specific shape. At runtime, when the code is actually executing, C++ is smart enough to look at the object and say, oh wait, this is actually a circle, and it will automatically call the correct specific draw function for a circle. One interface, many forms.
And this is the aha moment right here. We can have a whole list of shape pointers, but each one can point to a totally different concrete object. A rectangle, a circle, a triangle, whatever we want. We can then just loop through the list, call the exact same function on each one, and the right thing will happen every single time. That is the superpower. One interface controlling many different forms. It makes our code incredibly flexible and so much easier to expand later on.
Okay, let's bring it all home. What's the big takeaway from all this? How should you really start to think in objects?
It really boils down to this. You use association, the has-a relationship, when you're building something complex out of smaller parts. You use inheritance, the is-a relationship, when you want to create a more specialized version of something that already exists. Once you master these two ideas, you unlock polymorphism. And that is the absolute key to writing flexible, powerful, and reusable C++ code.
So you've got the tools now. You can model pretty much any system in the world. The building blocks are just these simple is-a and has-a ideas, but what you can build with them is truly limitless. So, the only question is, what are you going to build first?